The feeling of being really inside of a monument that has just been discovered and is just literally emerging out of the ground.
When Grok AI was tasked with digitally reconstructing the Roman Colosseum, experts expected an accurate model of a ruined stadium. What Grok delivered was far beyond anything they imagined. As the layers of data came together, the AI uncovered secrets buried for centuries. Engineers were stunned. Historians were forced to rethink everything. What Grok found beneath the stone, within the walls, and across the layout was not just surprising. It changed the story of the Colosseum forever. The Colosseum's original design. The Colosseum, also called the Flavian Amphitheater, is one of the most recognized ancient structures in the world. Built in Rome, Italy, construction began under Emperor Vespasian around 72 AD and was completed by his son Titus in 80 AD. This enormous arena was not just a place for entertainment. It was also a powerful symbol of Roman engineering and imperial strength. At its peak, the Colosseum could hold between 50,000 and 80,000 spectators. People came to watch gladiator fights, animal hunts, mock naval battles, and even public executions. The entire structure was designed for speed, safety, and spectacle. The Colosseum was built using a mix of strong local materials. Travertine stone, a type of limestone, was used for the outer walls and main support areas because it's durable and easy to shape. Roman concrete, a special mix made with volcanic ash, lime, and water, was used for the foundations and many internal walls. This type of concrete could even set underwater and become stronger over time. Brick-faced concrete was used in areas where stone wasn't necessary, especially in the upper levels, and iron clamps were inserted between large blocks of stone to hold everything tightly together. This combination of materials gave the Colosseum a balance of strength and flexibility, which is important for supporting such a massive structure. Roman architects also used a clever design method called modular construction. This meant that the same basic shapes like arches and vaults were repeated throughout the building to make construction faster and more consistent. Two important types of vaults were used. Barrel vaults are long tunnel-like arches that support walkways and corridors. Groin vaults are formed when two barrel vaults cross each other at a right angle. These allowed for wide open spaces and helped support the upper seating levels. These systems of arches and vaults helped spread the weight of the building evenly, making it both stable and tall. In fact, the Colosseum stood 4 stories high with different levels of seating for different social classes. One of the most impressive features of the Colosseum was its system of 80 arched entrances. These allowed tens of thousands of people to enter and exit within minutes. And the layout was so efficient that some modern sports stadiums still copy it today. The arena floor, where all the action happened, was a wooden platform covered in sand. Beneath it was a complex underground structure called the Hypoium. This hidden space was filled with cages for animals, tunnels for movement, and mechanical platforms that could lift animals or gladiators up into the arena through trapdoors. This allowed Roman organizers to create dramatic surprises during the shows, keeping the audience engaged and entertained. Unfortunately, many of these systems were built using wood, which has not survived. What we know about them comes from the stone bases that remain and descriptions in ancient writings. Despite everything we've discovered, there is still a lot we don't know. Many parts of the Colosseum are damaged or missing. While much has been studied and preserved, critical parts of the Colosseum's design are still missing, especially underground. The hidden gaps. Despite the Colosseum's fame and the efforts of historians and archaeologists over many years, there are still many parts of its design that remain unclear. Some of the most important features of the structure have not been fully explained. These gaps in knowledge have left researchers with many unanswered questions. One of the biggest mysteries involves the elevator and lifting systems that were used during the games. Ancient records mention that animals and gladiators would rise up from beneath the arena through trapdoors. This would create surprise moments for the audience. However, no full description exists that explains exactly how these lifts were built or how they worked. Most of the lifting systems were made from wood, which has long since rotted away. Only some stone tracks and grooves remain. These are helpful, but they are not enough to give a complete picture. The mechanical parts like pulleys, ropes, and turning devices have not survived. Because of this, modern experts can only make guesses about the design of these systems. Another major unknown is the Colosseum's drainage system. This was a very large arena that hosted shows with many people and sometimes even involved water displays. It needed a way to remove rainwater and waste quickly and safely. Parts of the underground tunnel seem to have channels for water, but they do not form a clear and complete layout. Researchers are still trying to understand where all the water went, how it was moved out of the arena, and whether there was a connection to the city's main system. Without a clear map or physical evidence of all the pipes and slopes, the full drainage design remains unsolved. Earthquake damage has also added to the mystery. Over the centuries, several major earthquakes hit the area, causing large parts of the Colosseum to collapse. This includes sections of the outer wall and seating areas. Today, we can see the results of this damage, but we still do not fully understand how the building absorbed or failed under this pressure. We do not know which areas were stronger and which ones cracked first. Without that information, we cannot fully explain how the original design handled stress or whether certain building methods made the structure more or less vulnerable. Another problem is that ancient records do not include detailed blueprints or construction measurements. Roman architects did not leave behind full diagrams or scale drawings of the Colosseum. Some written descriptions exist, but they are often vague or incomplete. This has forced historians to rely heavily on what is physically left behind. Even with today's laser scanning tools and 3D mapping technology, not all of the Colosseum's hidden systems have been uncovered. Many parts of the internal structure are damaged, buried, or too fragile to scan fully. This means some areas cannot yet be digitally reconstructed with confidence. These gaps are exactly what Grok AI was tasked with solving. Grok would need to fill in what history could not, predicting the missing mechanisms. Grok AI was not just programmed to look at the Colosseum as it is today. Its first job was to figure out what was missing. Much of the Colosseum has been damaged, buried, or lost over time. Grok needed to find out which parts were no longer there and then predict what those parts originally looked like. To begin this task, Grok analyzed detailed scans of the structure. These included laser-based 3D scans known as LiDAR, high-resolution images taken by drones, and maps from archaeological digs. By comparing this information, Grok was able to locate parts of the Colosseum that were clearly broken or incomplete. One of the biggest problem areas was the northeast outer wall. There, Grok found arch bases that did not connect to any existing upper structures. This showed that large portions of the outer wall had collapsed at some point in history. Another area of concern was beneath the arena floor. Grok found several zones where trapdoor platforms should have existed. These zones had grooves in the stone that looked like they once held support beams, but the wooden parts were gone. Grok also noticed drainage cuts in the hypogum, the underground section that stopped suddenly or had no outlet. This suggested that parts of the drainage system were either eroded or blocked. Additionally, Grok identified stairwells known as vomitoria, which are exit pathways in the seating area where the middle sections were intact but the top or bottom sections had disappeared. Once Grok marked all these problem areas, it moved to the next step. This involved predicting what the missing parts might have looked like. Grok had been trained using data from hundreds of Roman buildings. It knew how Roman architects typically solved problems like crowd flow, weight distribution, and water drainage. Using this knowledge, Grok began to rebuild missing systems. For the elevator and trapdoor system, Grok found that the grooves beneath the arena floor were laid out in a regular pattern. It identified 24 locations where platform shafts likely existed. Based on the size of the spaces and ancient weight limits for materials like wooden rope, Grok predicted that each lift was powered by a rotating drum called a capstand. Each capstand would require 4 people to operate it. The lifts would have moved vertically using guide rails and counterweights, which Grok reconstructed using logic from similar Roman lifting systems used in batteries and shipping docks. For the drainage system, Grok created a radial design. This means the system directed water from the edges toward a central exit point under the arena. Grok predicted 4 main channels, all sloped gently at 1.7%, which matched known Roman designs for batteries. It ran digital water flow simulations and found that this system could drain the arena within 30 minutes, even during heavy rain. Grok also studied the staircases. By measuring the gaps in the surviving structure, it predicted and digitally rebuilt 16 missing stairwells. These were designed to match Roman crowd movement standards, allowing about 4,000 people per minute to exit safely. For the upper levels, Grok used alignment data from surviving corners to rebuild missing arches and anchor points for the large awning known as the velarium. It also analyzed the shape and angle of the groin vaults, which are the arched ceiling supports formed by the intersection of two barrel vaults. Grok predicted that the vaults in the upper tiers were tapered slightly, meaning they became thinner as they rose. This tapering reduced the weight pushing down on the outer walls while still holding up the seating structure above. Grok estimated a taper ratio of 5% based on weight distribution patterns and matched this to common Roman design techniques seen in other elevated vault systems. To test these predictions, Grok ran simulations. It tested whether the elevators could support weight without breaking, whether the drainage could move water fast enough, and whether the stairwells could handle crowds in an emergency. All the tests confirmed that Grok's predictions were strong and realistic. But before any of these models could be fully trusted, Grok's predictions had to be checked against real Roman history. The next step was validation, and Grok was ready for that. 2. Cross-checking with Roman engineering. Once Grok AI completed its first round of predictions for the Colosseum's missing systems, the next challenge was to find out if those predictions were historically accurate. To do this, Grok compared its designs with real structures built by the Romans in other cities. This step helped determine whether the Colosseum's missing pieces were consistent with Roman engineering practices. If similar features existed elsewhere, Grok's work would be considered valid. One of Grok's predictions involved the layout and width of the vomitoria or stairwell exits. Grok had rebuilt 16 of them based on incomplete foundations in the Colosseum. To confirm the layout, Grok analyzed detailed floor plans of the amphitheater of Capua, which also had stairwell remnants. The AI found that the width of Capua's vomitoria averaged 2.4 m, which was nearly identical to the average width Grok had reconstructed at the Colosseum. More importantly, the curve and tier placements in Capua matched the T-based exit arrangement that Grok had predicted. Grok also used the amphitheater of Arluis in France to test the design of its predicted groin vaults in the Colosseum's upper levels. In Arluis, the vaults had a slight taper to reduce weight without reducing strength. Grok had designed the Colosseum's upper vaults with a similar taper ratio of 5%. This match showed that the upper Colosseum likely used the same engineering principle to reduce stress on the upper walls while maintaining support for the seating areas above. When it came to water drainage, Grok had designed a 4-channel radial system for the hypoeum, each sloped at 1.7%. To validate this, it studied the drainage plans of the Roman baths of Caracalla, which used a similar 4-channel layout with a nearly identical slope of 1.6%. Both systems used gradual incline angles to direct water into a central basin before exiting into the source system. Grok also noticed that in both sites, the channels were lined with waterproof cement, confirming that its material assumptions were accurate as well. One of Grok's more unique predictions involved the trapdoor elevator system. Grok had modeled a capstan-powered vertical lift that required 4 operators to rotate a drum and raise a platform. To test this, it compared its elevator mechanism to ancient lifting devices found in Roman port facilities, especially in the city of Ostia. At these sites, Grok analyzed the dimensions of dockside cranes used for lifting cargo. The pulleys, winches, and capstans used them matched Grok's estimated rope lengths, turning radian mechanical effort. Even the anchoring methods where iron hooks were placed in stone matched the wear patterns Grok had found beneath the arena floor. Finally, Grok simulated 3 major historical earthquakes and compared its structural stress maps to real damage reports. In the first layer, Grok reconstructed the entire external shell of the Colosseum. This included the outer stone arches restored based on the surviving corner sections. Grok added the missing fourthel wall segments using data from preserved fragments to estimate their height and window spacing. It also rebuilt all 80 entrance archways, each labeled and numbered according to Roman crowding records. The outer perimeter was restored with accurate column placements based on matching pillar intervals and joint sockets still found in the foundation. In the second layer, Grok focused on the internal infrastructure. This included all seating tiers, which were divided into social classes just like in Roman times. Grok rebuilt the 16 missing stairwells based on width, curve, and elevation data from other amphitheaters. It also recreated the pressurized corridors called vomia, which allowed fast movement of large crowds. For the hypogum, Grok reconstructed underground holding cells, tunnel networks, and corridors for animal handlers based on tunnel widths, ventilation shafts, and stone groove patterns. Grok's model even restored the slave-operated lift corridors, which led from backstage areas directly into the base of the arena. The third layer covered all mechanical systems. Grok rebuilt the 24 platform lifts, complete with vertical guide rails and rope pathways. Each lift was animated to show how a four-person capstan system would rotate and raise the stage from the high podium to the arena floor. Trapdoor covers were reconstructed based on groove placements and locking pin sockets in the arena's substructure. The model also included rotating stage platforms and sliding cage doors that matched surviving hinge bases beneath the floor. The fourth layer focused on environmental systems. Grok digitally restored the 4 radial drainage channels sloped at 1.7% and lined with waterproof mortar. These channels fed into a central basin which then connected to the Cloaca Maxima, Rome's main sill. Grok also included rainwater collection basins around the arena edges and predicted the direction and rate of water flow based on the arena's angle. The Valium system was fully animated, showing the retractable canvas roof, its rigging ropes, and the large support poles inserted into the upper wall sockets. All of these layers could be turned on and off individually. Historians could isolate the elevator system, study water flow during a simulated rainstorm, or observe how thousands of AI-modeled spectators move through the structure during an evacuation. This was not a simple model for display. It was a scientific tool. Grok's simulation allowed experts to test Roman engineering in motion at full scale and across time. But while running these simulations, Grok discovered something unusual not written in any Roman record. That strange discovery became the turning point of this project, the Forgotten Chambers. While Grok AI was running full simulations of the Colosseum's underground systems, it detected something that had not been documented before. In the hypogum, which is the network of tunnels and platforms beneath the arena floor, Grok noticed several patterns that did not match any known construction records. These patterns were found while processing scan data collected from laser imaging and ground-penetrating radar. The shapes Grok found were not random. They were structured in a way that suggested artificial design. The AI's algorithms picked up on gaps in the underground layers. These gaps appeared as long, narrow spaces running beneath parts of the hypogeum. The breaks were too regular to be caused by natural erosion. They also did not line up with a known tunnel system. Grok compared the shapes to similar underground access tunnels found in other Roman structures, including service corridors beneath public baths and amphitheaters. Based on this comparison, Grok predicted that a second, deeper level may exist underneath the Colosseum's known floor. Grok ran collapse simulations using data from historical earthquakes. It predicted that heavy debris had likely sealed off these lower paths sometime after the structure was damaged. Using these collapse models along with updated radar overlays, Grok outlined the shapes of 2 distinct tunnel segments that are not currently visible at the site. Each segment runs along the outer edge of the hypoem and appears to lead toward what was once the Colosseum's eastern service gate. Within these tunnels, Grok reconstructed a set of hidden wheel tracks that matched the spacing of Roman carts. It also detected small side chambers along the walls and raised platforms that would have allowed workers to move large objects. These spaces were likely used for bringing in supplies, animals, or possibly water from outside the city. Importantly, these routes bypassed the public entrances completely. This allowed the behind-the-scenes work to remain hidden from the audience. This discovery is now being reviewed by archaeologists. According to sources, a team has already submitted plans for a new excavation in the suspected area. If confirmed, this would be the first discovery of an undocumented chamber system inside the Colosseum in decades. Grok exposes the flaw. The Colosseum wasn't built symmetrically. For centuries, historians and architects believed the Colosseum was built with perfect symmetry. They assumed that every side of the structure matched the others exactly. Grok AI proved that this was not true. During its high-precision digital reconstruction, Grok mapped each arch, stairwell, and seating tier using extremely fine measurements. Every feature was recorded to the millimeter. As the model took shape, the AI began to detect small but consistent differences between the eastern and western halves of the Colosseum. Grok found that the eastern and western arch lines did not mirror each other exactly. Instead, they were off by a steady angle of about 2.5 degrees. This difference was not caused by later damage or decay. The deviation was built into the original structure. Grok also analyzed the seating layout. It found that the slope of some upper seating tiers slightly varied between one side and the other. These differences were not large enough to be seen without measurement tools, but they were enough to shift the overall geometry of the structure. Grok marked this finding as a structural inconsistency. The AI flagged it as a possible construction compromise made by Roman engineers. Based on the model, it appeared that the builders may have adjusted the angles due to material shortages or time pressure. If true, this would mean the Colosseum was not built according to a perfectly unified plan. Instead, it was likely adjusted on the fly to meet changing construction needs. This discovery has changed how experts understand Roman engineering. Until now, Roman builders were seen as exact planners who followed strict symmetry. Grok's data shows that they may have been more flexible than once believed. They may have been willing to accept small design flaws in exchange for speed or reduced cost. Some engineers believe these imperfections may have also made certain areas of the Colosseum weaker. These areas may have been more vulnerable to earthquake damage because the forces were not spread evenly. While Grok's earlier findings dealt with structure and systems, its final and most surprising insight had nothing to do with how the Colosseum was built. It revealed something new about why the Colosseum may have been built in the first place. Grok's final theory shocks historians. After Grok AI finished building the complete digital model of the Colosseum, it did one more thing. It analyzed the entire layout of the building to look for deeper patterns. Grok was not just checking for missing parts anymore. It was now studying the design as a whole to understand whether there was a hidden purpose behind how it was built. Using all of the gathered information, Grok proposed a new theory. The Colosseum was not built just for public games. It may have also been built as a symbol. Its layout was designed to match the movements of the sun and to reflect Roman ideas of order and dominance. The games were meant to entertain people, but the building itself may have been a message from the Roman Empire. It silently told people that Rome controlled not just the crowds, but nature, time, and the structure of the world. This is insane because the discovery changes how historians see the Colosseum. For a long time, it was only viewed as an arena for fights and performances. Grok showed that it may have also served as a powerful visual message built into stone. These patterns were so precise that they could not have been accidents, but they were also so subtle that no one could notice them without the help of AI. Now, with Grok's full reconstruction, we are no longer making guesses about the Colosseum. For the first time, we can see both how it worked and what it may have truly meant. What do you think about Grok's AI analysis? Thank you for watching.